Investigating rocks and their minerals enables geologists to sleuth their way back into Earth's history to better understand the evolution of our planet. It also enables the applied sciences and their related industries to locate and extract energy and mineral resources that are needed for agriculture, communication technologies, electricity generation, and transportation. Investigation occurs through physical and chemical analysis, using both simple and complex tools. One of the more complex tools is a petrographic microscope, also called a polarizing microscope. It's used in the field of optical mineralogy. Petrographic microscopes differ from other microscopes because they supply polarized light. This kind of light reveals many characteristics of the minerals contained within rocks. Observing a rock under a petrographic microscope requires creating a thin section. Scientists create thin sections by first cutting and then grinding a piece of rock to 0.03 millimeters thick, which is 30 microns or 30 millionths of a meter. The thin section, which is glued to a slide, is then placed on the microscope's stage. The stage can rotate, which is a critical feature of any petrographic microscope. A light bulb beneath the stage emits unpolarized white light, the wavelengths of which vibrate in many directions. This light then passes through the microscope's lower polarizer. The lower polarizer filters the light, constraining it to vibrate only within a single plane. Thus, the light becomes plane polarized. The plane polarized light then passes through the microscope's stage and the thin section. Observing minerals in plane polarized light enables us to observe opaque and non-opaque minerals, crystal shape, cleavage, color, and relief. Petrographic microscopes also have upper polarizers, sometimes called analyzers, that are located above the microscope's stage. The upper polarizer is a filter oriented 90 degrees to the lower polarizer. Since the upper polarizer's orientation is perpendicular to the lower polarizer, if no specimen is on the microscope's stage, then no light enters the eyepiece, and the resulting view is black. However, if a thin section is located on the stage, some light does pass through the upper polarizer. This allows us to view minerals in crossed polarized light. Depending on a mineral's refractive index, which is a measure of how much light bends as it passes through a mineral, some minerals appear black under crossed polarized light as we rotate the microscope's stage. These are called isotropic minerals. Examples of isotropic minerals include fluorite, garnet, and halite. Most minerals, however, exhibit shifting colors as we rotate the stage. These are called anisotropic minerals. Examples of anisotropic minerals include calcite, corundum, gypsum, hornblende, muscovite, potassium feldspar, and quartz. To observe the anisotropic mineral calcite, I recommend watching the video in this series named Sedimentary Rock Coquina and its Thin Section. In addition to discerning isotropic and anisotropic minerals, observing minerals in crossed polarized light enables us to view a mineral's extinction and twinning characteristics. Extinction occurs when a mineral transitions to a darker color, or even black, as the stage is rotated. Some minerals exhibit extinction angles parallel to the crystal's long axis, while others exhibit extinction angles inclined to the crystal's long axis. To observe extinction, I recommend watching the video in this series named Sedimentary Rock Sandstone and its Thin Section. Twinning occurs when adjacent crystals of the same mineral grow symmetrically and share some of the same crystal lattice. Twinning often appears as lighter and darker shades of the same color as one twin inclines toward or away from extinction. This creates a striped appearance and is the result of different crystallographic orientations of the twinned minerals. Twinning may appear parallel to the length of a crystal and be wide or narrow. It may also occur perpendicular to the length of a crystal. Some twinning patterns intersect at 90 degrees and look like a tartan or plaid pattern. To observe twinning, I recommend watching the video in this series named Igneous Rock Rhyolite Porphyry and its Thin Section.